So pulse width modulation, or PWM, is a very common microcontroller peripheral. So a PWM peripheral outputs a periodic waveform which can be controlled by changing the frequency and the duty cycle of the waveform. So PWM is commonly used to control the brightness of LEDs, control the shaft angle of servo motors, and also control the speed of motors, amongst other things. So this peripheral, rather than being just a logic 1 or a logic 0, like a GPIO peripheral, this actually outputs a periodic waveform. So we'll look at this block diagram here. We can see again we've got the core, memory, and so on. The PWM peripheral is a separate circuit completely, and it's connected via this advanced peripheral bus, then through the AHB to APP bridge, through this AHB matrix. So that's what enables it to connect to the core. So inside this PWM peripheral, and those various registers and so on, which we use then to configure the frequency and the duty cycle and so on. Some terms of the embed, we can see these are the 6. So before we had 5 to 30 are all GPIO, but we've not got that many GPIO, that many PWM. We just got these 6 down here. So P21 to P26. So these are the actual pins we can use for PWM. But I think also these LEDs as well, you can use PWM as well. So the pins the LEDs are connected to are also PWM enabled. So in this memory map, we can see, so this is the location of the PWM registers. So the registers live within these address ranges. So by writing values to those registers, you can configure the behavior of the PWM. So just looking at a PWM waveform. So this is a periodic waveform of frequency f. So we can also specify in terms of a period. Frequency is related to so reciprocal of the period. And then the ratio of the on time to the period is known as the duty cycle. So the duty cycle is given by the pulse width, so the period of the pulse width, so that's obviously this bit here, divided by the whole period. So obviously this periodic waveform, because here we can see 3 periods of the waveform, but this will just continue as long as the PWM switched on. So that gives us a duty cycle. So for this example, it's probably about 30%, I guess, looking at that. So it's probably on for about 30% of a period. And then obviously for a 50% duty cycle, there's got to have equal on and off times. So, essentially like a square wave. So that would result in half brightness for an LED and half speed for a motor. Because you can obviously control this. It could be completely switched off, 0% duty cycle, then maybe 10%, 20%, say 30. So that's going to be 50. Keep going up, and essentially when you get 100% duty cycle, it's just switched on for the entire period. So by sweeping through that, you can control the brightness, control the speed of a motor, and so on. So the NXP LPC 1768 has up to 6 PWM outputs. So pins 21 to 26, and actual embed pins as we saw before. So this is actually, the PWM works, it's based upon a 32-bit timer or counter with a 32-bit prescaler. And then there's several registers which control this. So we've got a register called match register 0. So this controls a PWM frequency. So for example, this is just showing one period here. So in this example, we've set the match register to 0. So this is going to essentially count, this timer or counter what controls the PWM it's going to count up to 100, and then when it gets to 100, then it'll kind of reset and define the start of a new period and so on. So match register 0, that's essentially the value where it starts a new period. And then you've got match registers 1 to 7 control up to the 6 different outputs, and the values that we write into those registers, they're the ones, they essentially control the duty cycle. So in these examples here, so this will be, say, for match register 1, we've assigned a value 75. So when the timer counts up, it's going to, the period starts off at a 1, it's going to count up to, and then when it gets to 75, the output will clear and it'll go 0. So this is essentially, because we've set 100 to be a match register 0 value, this is going to correspond to 75% duty cycle. Match register 2, we've written a value of 50 to that register, so this timer is going to count up. When it counts to 50, then it'll reset, so it gives us a 50% duty cycle. And then finally match register 3, so this is 25, we've written the value 25 to there, so it'll output a 1 until it counts up to 25, then it'll reset. So match register 0, match register 0 controls the period, and then the other ones control the duty cycle. So these are all based on the value, these are just values that it counts up to, if you will, but the speed at which it counts is controlled by this prescaler and the actual clock frequency of the microcontroller as well. So you also need to, you need to know what your clock frequency is, set a suitable prescaler, and then when you've done that, you can figure out what values you actually need to write here.